Hello everyone, this is Jingyu and Yuntao. Today we are going to talk about paper number 8, a comparison of string metrics for matching names and records. This paper was presented on the 2003 Knowledge Discovery and Data Mining Workshop on data cleaning and object consolidation. Today's presentation will be conducted in 5 parts. I will first give a brief introduction about the background work and the second string toolkit, and then go through different metrics for computing string distances and show some examples of the dataset they use. Next, Yuntao will talk about the experiments and results. So, the task in the context of this paper is the entity name matching problem, which is given two entity names or two strings, how can we come up with a metric to decide whether the two names match each other? Different entities have given different formulations and solutions to the matching entity names problem, and the detail of their formulation are shown in different blocks in this slide. So these communities have emphasized more on developing autonomous techniques, and what they did not do is implementing a toolkit of methods that can be easily applied to new tasks. Thus came the motivation of the presented work today. So in this presentation, the author of the paper and the team have together implemented an open source Java toolkit named SecondString. You can follow the link here and download the source code to play around with it if you're interested. In SecondString, various metrics for computing string distance are introduced, and experiments are conducted on different metrics to test their performance. Our fundamental type of object in SecondString is the distance function. A distance function will simply take two strings s and t as input and output a real number d that measures the distance between string s and string t. There are three types of distance metrics used in SecondString, and they are added distance-like functions, token-based distance functions, and hybrid distance functions. Added distance-like function use added distance to measure how far away string s is from string t. And added distance means the cost of best sequence of added operations that can convert string s to t. Added operations are basic operations on string, such as deletion or insertion of characters. For example, to convert string s apple to string t people, we need to perform the following added operations of deletion or insertion. We can assign different costs to each type of operation to generate more complex distance metrics. In Levenshtein distance, which is the simplest added distance function, unit cost is assigned to all added operations. While for Jerome matrix, the distance between string s and t are calculated using the number of characters in one string that is in common with the other string, as well as the number of transpositions. The second type of distance matrix is the token-based distance. In this type of distance, each string s is viewed as a multi-set of words. For example, given a string master of computational data science here, we first need to transform it into a set where each item is a word in the original string. Then, Jacquard similarity will simply compute the size of the intersection set between s and t divided by the size of union set between s and t. While for TF-IDF or cosine similarity, we will use the TF-IDF score of words in the intersection set between s and t to calculate the distance between string s and string t. One important contribution of the paper is that they came up with the third type of distance matrix, the hybrid distance functions, which actually combines the previous two types of metrics. So soft TF-IDF is one of such distance metrics. We can see that comparing with the previous TF-IDF formula here, they have added a third item, the NUT, which is computed using another similarity function sim prime. In this experiment, they used Levenshtein distance for sim prime. So by doing that, we actually combine added base distance with the original TF-IDF, which is the token-based string distance. So the dataset they use are they have used 11 different datasets from various sources, and most of the dataset contain lines of entity names like shown in the right table here. So the first column is the relation from which this example comes, and the second column is the ID of this entity. In this case, is the URL here. And the third column is the entity name, which is the thing that we need to match. So if the two entity names share the same ID, we will count them as matched. So the ID here will serve as a ground truth label when we test our string distance matrix. Note that census is a different data set from comparing with the other data, and this will lead to different experimental results, which will be introduced by Yuntao in the later part of the presentation.
Okay, let's move on to the experiment part. Before we go to details to the experiment, I want to first clarify two concepts. These are precisions and record. As you can see in the graph, precision is the true positives over sum of true positives and false positives, and record is the true positives over sum of true positives and false negatives. You can treat precision as a measure of quality or exactness, and record as a measure of quantity or completeness. And our experiment will illustrate the interpolated precision record curve and max F1 plots of different matrix functions. So now assume we have a small data set that streams A to G by applying block algorithm, which is detailedly explained in Cohen's previous paper, and we will get some candidates pairs of strings. So basically, the blocking algorithm is to reduce the candidates pairs of streams, and we want the pairs with common substrings that are not too frequent in our stream names. So now we have this reduced set of candidate streams, or pairs. Then we can parse them to our matrix functions, such as soft TF, IDF, to get their corresponding scores of, or we call the similarities. So before we go further, I want to introduce the difference between non-interpolated and interpolated graphs. The non-interpolated 11 points precision record curve has a sawtooth-like shape. Because the same record, the precision will drop for the next retrieved instance, which is not relevant, or I mean not positive. But for the interpolated, we define the precision P interp at the record level R as the highest precision for any record level R prime, any level R prime, not less than R. And I will next explain it with a more friendly way with simple examples. So let's see our long interpolated one. After parsing the candidates pair to function f, we get them ranked with their scores. And we already have their labels to show they are matched or unmatched. The long-interpolated average precision is defined as a formula here. N is the number of candidates, and M is the number of the matched pairs. Ci is the number of correct pairs ranked before position I, and delta I is 1 if it is correct at position I, and 0 otherwise. So for this example, we have the non-interpolated average precision as shown on the right. However, for the interpolated one, we have the same settings here. But now we define the interpolated precision at record level R, the max among all Ci over I, where Ci over M must be no less than the record level R for all the qualified ranks I. For example, at the record level, R equals 0.5. We have the following terms. The qualified ranks I are 5, 6, and 7. We only need to check the qualified part below green lines, among them to the high, and among them the highest is 5 over 6. So 5 over 6 is the interpolated precision at record level R equals 0.5. And as you can see, as the record level increases from 0 to 1, we will have a smaller pool of precision to be selected. So interpolated precision record curve is a non-increasing curve, and it will be demonstrated in the next page with 11 record levels. Here is the performance of edit distance measure on the left, token-based measure in the middle, and hybrid measures on the right. As you can see the red curves in the graphs, the Morgan-Elkin, TF-IDF, and soft TF-IDF performs the best in their corresponding type of measures. So overall, soft TF-IDF performs the best, as you can see on the left graph. And besides, compared to the nerd-metric function, soft TF-IDF only get defeated at the very extreme record level R equals 1. So I also downloaded the soft TF-IDF toolkit and run codes to get some demos for the string matching. And you can pause these videos to see these examples, and you can find something interesting. I want to talk about is this one. We can see the blocking algorithm in the examples in the middle. Research is a frequent substring in this dataset. So the width for the research is really low, and you can see the similarities here is therefore kind of low. I also include a personalized pair of strings, as you can see here for the last one. So besides the two types of curves introduced above, max F1 is also used for demonstration of this experiment. F1 score is defined as this formula here. You can pause and check it. And here is a max F1 score of Levenstam compared to that of the soft TF-IDF. Each dot here is a max F1 score of a certain dataset. For most of the datasets, soft TF-IDF performs better than the Levenstam, you can see here, and except the one here. And this is a census dataset, which has a non-trivial structure with categories besides normal names streams, which we call the records. And here's a table for performance of various structure exploiting methods on census. Cohen also combined the SVM binary classifiers in it. All of them improves over the bare soft TF-IDF, and the Levenstam-Winkler performs the best. So based on all the experiments we talked about, we have some findings. First, stream distance are not suitable for all the comparing entities with non-trivial structure, such as census dataset with records. So we need to apply some extension to the toolkit which allows records to be compared. For example, the one is the Levenstam edit distance metric, modified by the Winkler for gyro distance metric with scores being adaptively combined by SVM binary classifier. And this can improve over the soft TF-IDF. And the result is that the non-interpolated average precision is improved from 0.782 to the 0.951. Thank you for watching these videos, and this is all for this presentation.